start recording.
Where's Yovan?
I don't know. He's probably sleeping. All right, welcome to the third mechanical meeting. It's not going to be uh, as packed as last week, so I just want to show you guys some things. So, update. So, I went to Richard's house on Wednesday to disassemble the chassis and count all the parts that we had, and I got hella mosquito bites, fucking staying outside, but it was worth it. So yeah, counted all the pieces. I actually didn't include some of the brackets just because these are really specific to the old chassis, and I don't think we need it.
And we water jetted those.
Yeah, yeah, we actually had a lot of stuff that we didn't use from last year, such as the suspension. I I know you guys spent a lot of time on that, but I
That hurts me every time you say that, man. You have no
yeah,
idea.
I know you guys spent a lot of time on that.
And I messed up on threads.
Not gonna lie, I was expecting this.
Yeah, so I don't think future designs really need the suspension. I
It's
think we
just an
just need
accessory.
to, yeah, it's more of an extra, and I actually think since we didn't test it yet, um, we don't know how it's gonna be like, and it's also really specific to the old chassis, and um, you can't move it to the new iteration. So yeah, Richard and I just agreed that we shouldn't use the chassis and Yovan as well. I mean, use the suspension. Yeah, and so I'll be talking about like just the wheels, the aspects of the wheels in the robot on the chassis. So I think last year we actually saw that some designs actually had 3 wheels instead of 4, and I didn't know why they would do that. Um, but yeah, so if you have 3 wheels on a robot, it's actually more efficient in your on your motors, just because there's less rolling resistance. You have one less wheel, so you can actually go further with the same amount of batteries, same amount of wheels, but you just have like one passive wheel. Um,
That's
and
the
it's
wheels on the back, right?
yeah. So on this design right here, on this robot, I got it from the IGVC design report, and they actually have their passive wheel in the front. So this is known as a delta position. So if you look here, I drew the shape. So you can imagine there's, oh shit. Uh, can you guys see my mouse?
Yep.
Okay, so the wheels would kind of be at these endpoints. So you have the 2 motors in the back and one passive wheel in the front, right? So your center of gravity has to always stay within this shape here. Otherwise, it's going to tip over. So if you have 2 motors in the back, that's known as a delta position. If you have 2 motors in the front, that's known as the tadpole position. And yeah, and the tadpole position is much more stable than the delta. So you're gonna see a lot of like older 3-wheeled cars. They initially started with the delta position and then eventually moved to the tadpole position because it's more stable. And the reason why is because when you're turning, um, your center of gravity changes due to the angular impulse. So when you turn, this kind of shifts over, right?
Yeah, have you guys seen Top Gear?
Nah.
The
Oh, actually,
You think
I think I
yeah,
know what you're talking
three-wheel
about.
car? Yeah, yeah. All right.
Yeah, so like they had like a three-wheeled car, right? And then they were going like really fast, and then they turned, and then it flipped. Is it?
Yeah, yeah. It was a little red car or something.
Yeah,
So the thing I was thinking as well, if we're gonna have three wheels and your robot's actually that tall, that that that's gonna fall over like the London Bridge, bro.
yeah, and also it also depends on what speed you're going as well.
Well, we're only gonna be going 5 miles per hour, right? It's constant velocity.
Yeah, but when we're turning, that might be an issue.
Yeah.
But I
So,
think in this case, since the robots are kind of slow, you can actually have this design. It's fine.
so that design actually works.
Yeah.
Oh,
I mean, as long as if it doesn't tip over when it's turning, like that design is good, like no matter what. So I'm pretty sure that this design that they have here didn't tip over, so it still qualifies. It's just the exact same as this.
I think that front wheel would just get stuck in like the terrain. Though.
Yeah, yeah,
yeah,
because
on
you
the
have more
back.
weight on the front, right, on one wheel.
Yeah. You need to have the big wheels on the front. You have to have that small wheel on the back.
Uh, but yeah, there's like pros and cons to having three wheels versus four wheels. So just to keep that in mind. Um, and yeah. Do you guys think we can do three wheels? I think you guys think it's possible.
I don't want to give
I
it away, but our design is three-wheel.
yeah.
Oh, okay. Yeah. Yeah, you guys are
Hopefully, Jose was in this one.
right. Yeah. And also I forgot to mention, usually with three wheels, your body has to kind of conform to this shape. So you're gonna have a triangular shape, and it's gonna be much more aerodynamic. But I think on this one, they just put a passive wheel on the front. That's it. Yeah, you guys can see the LiDAR here on the camera and the light sensor. I don't know what these are. You have the payload on the bottom. Yeah. All right, cool. So these type of robots kind of use differential drive, which is basically we have two motors that drives the whole entire robot, and then you have passive wheels. So it's actually the most common control mechanism for robots. And the velocity difference between the two motors can drive the robot in any path and any direction. So um, it's really useful to have a differential drive. I mean, there's other types of drives as well, but this is the most common one you guys are gonna see. And there's three types of turns, but we're only gonna focus on one. But I just want to get you guys. I just want to introduce you guys to the other two. So the other two is called the point turn, and it's where you just kind of turn on the spot, and you can calculate this by the rotation is equal to n divided by 360 times your track width, which is the space between the wheels, times pi divided by the circumference of the wheel.
And the circumference of the wheel is gonna be affected by the torque you need, right?
Uh,
Because the more torque you need, the bigger the wheel.
technically,
Wait, no, the more bigger the wheel, the more torque. Never mind.
yeah, yeah, but in this case, it doesn't take into account the torque. It's
Okay.
just the rotation. Yeah,
Okay.
yeah. And then this is what's known as a pivot turn. It's essentially where you have one motor on, so it kind of pivots on one wheel, And the formula is the exact same, except that on the second formula here, you just do, you multiply by 2 on the top. So you can think of it as a circle here, right? And on the previous one, it's a smaller circle. Yeah. Okay, so a curved turn. So this is where the both of the motors have different velocities. So you have different um, turn rates. Um, so this is actually much more complicated. And I was trying to look into it, and I found this website here that I want to show you guys.
Kinematics.
Yeah, this is like different kinematics. It's more like position based. So the
Yeah.
kinematics you learn in physics is like with the projectile, right?
Yeah. Projectile motion.
Yeah,
Free.
and this one
All of
is
that.
more towards
Objects in motion.
yeah, like turning and just
Yeah.
the position of the turn, stuff like that.
Yeah.
Um, I don't want to go too deep into it, but it's really, if you guys can see, it needs a lot of calculations. Um,
Cross product. What the heck? So many determinants.
yeah, because it's your turn is based off of your time, your position, and your velocity. So if we want our system to be dynamic like this, you see how it's doing a loop here and then it's curving. You have to take into account all these different factors, and you have to deal with a lot of matrices.
When you say dynamic, I know static is when your system or your body isn't moving at all. But when you say dynamic, what are you referring to exactly?
Um, Dynamic as in it changes.
Oh, okay.
Yeah, it just changes as you drive the robot. Because
Oh, so it's constantly changing. Okay.
yeah. So I mean, I don't think we're gonna do something like this, but so for the state machine team, we're gonna have to help them out on the turning, on
Yeah.
calculating the turns, because uh, yeah, if we want it to move in a certain direction, you have to calculate the angle of the turn, and
Wait,
this is
Tim.
yeah. What's up?
Way back. I found a source. I know this.
Yova's here.
Be quiet. Anyways, I'm kidding. I'm kidding. Anyways, I know the formula that you were able to find was in respect to angle of the turn. I
Yeah.
found one for both differential steering and pivot steering where it talks about the radius of the turn. And I feel like doing in respect to radius will probably be more beneficial for us. I'll try to find it if I can. If not, then whatever.
Okay. Yeah. That's good, Jovan. Yeah, I know this is like in rotations, right? And we want it in degrees. So
Yeah.
yeah, just you can put that in the chat when you find it, so we can all look at it.
I will not be able to find it today. Or
That's fine.
sorry, during the meeting.
Okay. Yeah, that's fine. But yeah, so I just want you. I want you guys to get introduced to this. It's
Six
not as
determinants, bro.
yeah.
1, 2, 3. Yeah, 5 determinants.
Yeah. So you don't have to focus on this for now. We're gonna probably do all the calculations after we pick the iteration. Oh, all right, cool. So SolidWorks example. Um, Actually, before I start this, actually, never mind. I was gonna ask Jovan, but Jovan, do you want to show? Uh, have you started on the iterations yet?
Like the new iterations, no, I haven't. And even if I did, I'm on Mac OS, not on Windows. So I'm gonna have
Okay.
to restart my computer. My bad.
Yeah, that's fine. Yeah, I just want to show you guys what I did. So for example, let's see. Just to give you guys an idea on how to put everything together. Where's hide? Am I blind?
At the bottom. Oh, up top, up top, up top. The eye.
Oh my god. All right. Brackets. Acrylic. All right, cool. So when you guys are assembling the parts together, first you want to start off with the T-slots, right?
Of course, yeah.
And based off of this design, I wanted to put the electronics compartment here, right? So first, I actually had my electronics compartment here, and then I mated the bottom T slot to this to the electronics compartment here. And then after that, I put all the rest of the T slots together here as such. And then after that, you have to put all the brackets together. So brackets are here. So once you put all the brackets there, we're gonna have to make sure that we have to cover this side with acrylic. So what I actually did was the acrylic pieces that we have are 12 by 24. And based off of this sheet, you're gonna have to make a like an acrylic sheet to cover that specific side here.
Hey Tim, can I ask a question?
Yeah, go ahead.
What's the tolerance?
The tolerance
Yeah.
for the laser jet?
Yeah.
It could literally. I don't know.
Because this is at 5 decibels right now. That's got to be a really tight tolerance.
Yeah, I'll actually get back to you on that because I'm not
Okay.
too sure. Yeah, this is also assuming that we can go to the makerspace next semester or something. Or I don't know how we're gonna do it, but I'll get back to you on that.
Because if we are able to go to the makerspace, wouldn't we all need to get clearance?
Pretty much, or we can just send one person there, and in terms of the laser cut or the laser jet, whatever.
Yeah.
Like one person could just do that. But if you're talking about like machining,
Yeah.
yeah, we'll just section that off to like two people at most.
Yeah.
But that's an if, so just hold off on that. And I'll talk to Richard about it.
Okay.
Yeah. But yeah, so I actually got the dimensions of the specific side here, and I made a shape around that. And all I did was extrude it.
How much?
1/8 of an inch.
Okay. Yeah.
And once you have that, and you have to make sure that you include spaces for screws.
Mm. What type of screw?
The same one we have for the T-slots.
Are they
All
thread?
you have to worry about is the size of the hole is 0.257. That's it.
Okay. So they're not threaded or anything. It wouldn't matter about that.
Yeah, just make sure the size is 0.257 in diameter.
Okay.
And then once you have that,
Wait, I'm out. I found it. For skid steering, aka pivot steering, it's on page 10.
I heard the enter when he entered the leap.
Okay, I'll take a look at that after.
No problem.
Okay, so once you have that, you can mate your acrylic onto the T-slot. Just gonna look something like this. And yeah, this is how it should look like when you guys put the design together. Yeah, and if you guys are stuck with anything, or you guys have an idea but don't know how to do it, make sure you reach out to us, either me or Jovan or Jose. Actually, not Jose, because he's doing his own design. I was kidding. But okay.
Jose's fat quiet right now.
Yeah, because I'm just chilling, bro.
Oops. Oops. All right. So your task for this week, keep working on the designs. These iterations must include all the mounts for the battery and the LiDAR, all the brackets. So we have to make sure that we know how it's gonna be placed and how it's gonna stick together. And then all the acrylic. So all the outside surfaces must be covered in acrylics so that we make sure that it's waterproof.
Yeah.
The wheels, so the motors and the passive wheel, and the LiDAR slash camera slash mechanical stop T-slot. So I'm not requiring you guys to make the mounts for these, just the T-slot where it's going to be placed, if that makes sense.
What What do you mean by mounts? Because I know the brackets are.
Yeah, so you know the battery that I gave you guys?
Yeah.
It doesn't have a mount. So I want you guys to design a mount so we can put the battery on
On
this
the T
mount.
stop.
So it's mounted on the T-slot. Yeah, exactly.
Okay.
I'm pretty sure we're gonna 3D print that mount for the battery.
Mm-hmm.
Um, yeah, depending on the size of the mount, we might have to cut it in half, or I might actually give it to Jovan because he has a bigger. Do you know someone who has a bigger 3D printer?
An industrial one, huh?
A big boy 3D printer. I'm kidding.
Yeah, and then I yeah I told you guys about the shorter deadline. I'll change
Yeah.
that to the 23rd, actually.
One more day.
Yeah, and I can't really gauge how fast you guys can finish the design, but by next week the iteration should be at least 80% done. And I know it's a lot, but essentially what I showed you from the SolidWorks example, it's just a lot of repetitive stuff. So
Yeah. A lot of mating too.
yeah, yeah, and you guys can use the mirror function to just create half of the robot and then just mirror it on a plane, and then
Yeah.
that should cut your time by like 40%.
That's
So
exactly what I was thinking right now.
yeah, yeah, that's it for this meeting. Um, yeah, just make sure you guys stay on top of it. I know it might be a little fast right now just because we have this deadline, but yeah, I'm 100% sure that you guys can do it. Yeah, that concludes this mechanical team meeting. Let's stop